Hello everyone, welcome back to the lecture series on magnetism in condensed matter physics. So we were talking about the isolated magnetic moments in the magnetic field. Until now we have discussed it about diamagnetism and paramagnetism. Now let's move on to a new topic, that is the ground state of an ion and the Hund's rule. Now a typical atom contains many electrons. A lot of these will be in the filled shells which have no net angular momentum. Like in the case of this particular p orbital, all the cells are completely filled. So in this case, the net spin angular momentum value is 0, as well as the net orbital angular momentum value will be equal to 0. So thus, in case of completely filled shells, the net angular momentum is 0. But if the cells are partially filled, then the net spin angular momentum may not be equal to 0, as well as the orbital angular momentum may not be equal to 0. So there will be a net angular momentum. So therefore, the orbital and spin angular momentum can combine in 2l plus 1 times 2s plus 1 ways. For a particular value of L, ML can take values from minus L to plus L, including 0. So therefore, there will be 2l plus 1 terms. And similarly, for the value of S, MS can take value from minus S to plus S. So here also there will be 2s plus 1 terms. So therefore, the two angular momentums can combine in 2l plus 1 times 2s plus 1 ways. Now these different configurations will cost different amount of energies. This difference in energy occurs because the choice of spin angular momentum affects the spatial part of the wave function. And the orbital angular momentum affects how electrons travel around the nucleus. Both therefore affects how well the electrons avoids each other and thus influence the electrostatic repulsion energy. As you must have studied in the quantum mechanics, that if S is equal to 1, then the spin wave function is symmetric and therefore the spatial part has to be antisymmetric. Whereas if the value of S is 0, then the spin wave function is antisymmetric and the spatial part has to be symmetric in order to follow the Pauli's exclusion principle. So in the case of multi-electron system, the orbital and spin angular momentum combine in a way to minimize the energy of the system. Now let's see how to find the configuration that minimizes this energy. So let's now talk briefly about the spin-orbit interaction. Consider an electron orbiting an atom. So in the frame of nucleus, the electron orbits around the nucleus. But in an inertial frame, co-moving with the electron, it is the nucleus which is orbiting around the electron. Now the orbiting nucleus constitutes a current which gives rise to a magnetic field at the origin equal to E cross V divided by C square, where E is the electric field at the electron due to the nucleus and VR is corresponding potential energy. So therefore we can write electric field in terms of potential energy as this equation 1 comes from the transformation of electric and magnetic fields in special relativity. So this magnetic field, it interacts with the spin of the electron to give a term in the Hamiltonian as minus half m dot b, where m is the magnetic moment associated with the spin and it is equal to G times E h cut divided by 2me and then the S vector. Here in this equation 2, the factor half is a relativistic Thomas factor. So if we substitute the value of m and b here, E h cut square divided by 2me c square r times dv by dr and then S dot L, where h cut times L is the orbital angular momentum and its value is equal to me r cross v. Now this effect is known as the intrinsic spin-orbit interaction and is an interaction between the spin and the orbital part of electron's wave function in an atom. Now the value of 1 divided by r del v by del r for the case of Coulomb potential is given by Ze divided by 4 pi epsilon naught times r cube, where I have used the concept of hydrogen-like atom for Z denoting the atomic number of that atom. Also from quantum mechanics we know that the expectation value of 1 divided by r cube in case of hydrogen-like atoms is equal to Z cube divided by a naught cube n cube into L plus half into L plus 1, where a naught is the Bohr radius. So therefore the spin orbit splitting is given by z raised to power 4 e square h cut square and then the expectation value of S dot L divided by 4 pi epsilon naught a naught cube n cube L into L plus 1 times L plus half. So therefore this spin orbit interaction energy is proportional to z raised to power 4 and therefore cannot be treated as a small perturbation for atoms with high atomic number. Now so far we have been kept the spin and orbital angular momentum separate since they were independent of one another. However, they do weakly couple via this spin-orbit interaction, which acts as a perturbation on the state with a well-defined L and S. Because of this, L and S are not separately conserved, but their summation, that is total angular momentum, is conserved. Thus, the state with L and S are split into a number of levels with different J values. This is known as the fine structure. Here, J can take values from L minus S to L plus S. Now, as J is equal to L plus S, so therefore, J square must be equal to L square plus S square plus 2 L dot S. So therefore, L dot S must be equal to J square minus L square minus S square divided by 2. Now, since the spin-orbit interaction energy is proportional to the expectation value of L dot S, so therefore the expectation value of lambda times L dot S will be equal to lambda by 2 lambda by 2 into J plus 1 minus L into L plus 1 minus S into S plus 1. Now the energy of this atom is mainly determined by the values of S and L via the electrostatic considerations. So the energy eigenstate can be labeled with the values of S and L. Now each level without the spin-orbit interaction is a multiplet of 2s plus 1 times 2l plus 1 states, and with spin-orbit interaction as a perturbation, the multiplet splits into different fine structure levels labeled by the value j. With degeneracy 2j plus 1, so that these levels can be split into different mj values by applying a magnetic field. The splitting of different fine structure levels follows a relationship known as Lande's interval rule, which says that the splitting between j and j minus 1 levels is proportional to j. Now let us consider the fine structure splitting in case of s equal to half and L equal to 1. So here 2s plus 1 is equal to half times 2 plus 1, that will be equal to 2. So there will be 2 spin states and 2L plus 1 will give you 2 into 1 plus 1, that will be 3. So therefore there will be 2L plus 1 times 2L plus 1 equal to 6 different ways in which L and S can combine. Also, as we have mentioned it, that for a given value of L and S, J can take values from S minus L mod to L plus S mod. With 2J plus 1 state for the J equal to half and 2J2 plus 1 for 3 by 2. So therefore we'll have 2 and 4 states, and in a total we have 6 states, which is the same result we got from here, 2s plus 1 into 2l plus 1. So the summation of 2j plus 1 from j equal to l minus s to l plus s will be equal to 2l plus 1 times 2s plus 1. Now let's see how we can represent this in the graphical method. Now let's see the coupling scheme for l equal to 3 and s equal to 3 by 2. So for that you need to make a rectangular grid of ml versus ms values. So here you can see in this particular column the value of ml is 3, and in this it is 2, then 1, 0, minus 1, minus 2 and minus 3. While in this row the value of ms is same, that is 3 by 2, and then in this row it is minus 1 by 2, and then 1 by 2, and then 3 by 2. So in this way you need to make a rectangular grid. Here you can see that there are total 28 states corresponding to 2s plus 1 spin state and 2l plus 1 orbital states. So if you couple them, then you can find the values of j as 9 by 2, 7 by 2, 5 by 2 and 3 by 2, and with the mj values from plus j to minus j. Here also in this pyramid you can see there are 28 states corresponding to 2l plus 1 times 2s plus 1 states. You can check for other values of L and S here. I will put the link of this particular simulation in the comment box, so please check it out. Now there are clearly a lot of combinations of angular momentum quantum numbers that are possible, but out of these, which one is the ground state for a particular ion? So that will be our question. So that question will be answered by the Hund's rule. The Hund's rule is used to estimate the combination of angular momentum quantum numbers. Now Hund's rule is used to estimate the combinations of angular momentum quantum numbers which are founded to minimize the energy. There are three empirical rules. In the first step, you need to arrange the electronic wave function so as to maximize S. In this way, the Coulomb energy is minimized because of the Pauli exclusion principle, which prevents electrons with parallel spins being in the same state, and this reduces the Coulomb repulsion between electrons. In the next step, given the wave function determined by the first rule, you need to maximize L. This also minimizes the energy and can be understood by imagining the electrons in the orbit rotating in the same directions can avoid each other more effectively, and therefore reduces the Coulomb repulsion. At last, the value of J is founded using J is equal to mod of L minus S if the shell is less than half filled, and J is equal to L plus S if it is more than half filled. This rule arises from an attempt to minimize the spin orbit energy. Using these rules, the ground state can be given by 2s plus 1 L of j. Here L is written not as a number but using a letter according to this sequence, and 2s plus 1 is the spin multiplicity. Now let us consider an example of dysprosium ion with outer shell as 4f9, so that the outermost shell has the f orbital with the ml values as 3, 2, 1, 0, minus 1, minus 2, and minus 3, so that the ground state will look like this. Now as L is equal to 3, so therefore 2L plus 1 will be equal to 7. So in this case, the total spin angular momentum will be equal to 7 times half for up spins minus 2 times half of for down spins, which will be equal to 5 by 2. So this means the spin multiplicity 2s plus 1 will be equal to 6. Now as the spin up electrons give no contributions to the orbital angular momentum, and according to Hund's rule we have to maximize the value of L, so the final two electrons will go into orbits with ML equal to 3 and 2, so that the total orbital angular momentum will be equal to 5. And since L is equal to 5, we will use the symbol H. Also, the shell is more than half filled, so therefore the value of J will be equal to L plus S, which will be equal to 5 plus 5 by 2, which is 15 by 2. So therefore the ground state will be 6H 15 by 2. The Hund's rule lead to a prediction of the ground state, but it doesn't tell anything about the excited states or how close they are to with the ground state. They therefore allow us to estimate the magnetic moment of an ion, assuming that only this ground state is populated. So till now we have considered the magnetic moment on each atom being associated with an electron, but in case of metals, the conduction electrons are not localized on a particular atom but exist in band states and are delocalized over the entire material. These conduction electrons can show both a diamagnetic and paramagnetic effects. You can check it out my lecture series on band theory of solids by pressing the eye icon on the right top of this screen. This is it for today, and in the next video we will talk about adiabatic demagnetization and hyperfine structure. Thank you so much for watching this video.